Okay, let's find a linear approximation to the function p of w d near the point when w is equal to 140 and d is equal to 3. And basically what this chart gives you is the blood alcohol percentage given a weight, W, and a number of drinks consumed, 3, as long as the drinking is done under 1 hour. So we want to find, we essentially want to use the tangent plane associated with the values in this graph near 140 and 3. We want to use the tangent plane to estimate P of WD. That's essentially what it means when it says find a linear approximation. Well, if your point of tangency is x naught, y naught, z naught, and your function is z equals f of x, y, we know what the tangent plane looks like. It looks like z equals the partial of f with respect to x, evaluated at x naught, y naught, times x minus x naught, plus the partial of f with respect to y at x naught, y naught, times y minus y naught, and then plus z naught, which is really just f of x naught, y naught. So what does it look like when we change f to p? Well, it doesn't look that much different. We're going to use this version of the tangent plane. We'll say that our linearization will use the L of x, y notation. And we'll say that that's equal to the partial of p with respect to w evaluated at 140. That's the w, that's the particular w value. And 3 drinks, 140 pounds, 3 drinks. Times w minus 140. So that's like your x minus x naught right there. And then plus the partial of p with respect to d, evaluated at 143. And then times d minus 3, plus the height value of the, essentially the point of tangency, which is p evaluated at 143. Again, this is essentially the equation of the tangent plane to the function p at 143, p of 143, which turns out to be 0.08, I guess. Okay, so basically what we need to do is estimate these partials using the values in the graph. Estimate these partials using the values in the graph and fill in this equation, and then we're done. So how do we estimate those partials? Well, let's do the first one. The partial of p with respect to w, evaluated at 143. If you think about it, that should be approximately equal to, well, let's see, what kind of delta can we use? It looks like the difference between the weight values is 10. So let's use a delta w equal to 10 here. And then let's use the difference quotient to estimate this. So it would be p of 140 plus delta w, which is 10, comma 3, minus p of 143, all over delta w, which is 10. Now you get these values by looking in the chart. This 140 plus 10 is 150. So if you go up and look in the chart, p of 153, comma 3 would be the 0.075 is what that says there. So I could rewrite this then as .075 minus, okay, p of 143 is the 0.08 number, and then divide that by 10. And just remember, the actual partial derivative is the limit of this as delta w goes to 0. But we can't take a limit when we're given discrete values in a chart. So we'll use the difference quotient to estimate the partial of P with respect to W at 143. If you compute this, you get the opposite of 0.0005. But wait, we can get perhaps a better approximation by taking delta W equal to -10 and then averaging. So we're gonna take a new estimate of the partial with respect to W by taking delta W equal to -10, so that the difference quotient becomes P of 140 plus delta W, but that's now -10 or plus a -10, comma 3, minus, again, P evaluated at 140 and 3. And then that whole thing divided by delta W, which is -10 this time. And if you look in the chart, this guy is, it's P of 130, comma 3. If you go back and look in the chart, okay, go over to 130, and then over to down from 3.087 is what you get. Okay, 0.087 minus 0.08 all over -10, and that turns out to be -0.0007. Now we're going to take the average then of these two values as our estimate of the partial of P with respect to W at 143. So take this partial to be approximately equal to the average of those two numbers that we just got, -0.0005 plus -0.0007 all over 2, and of course you get -0.0006. Okay, so that's our estimate of the partial of P with respect to W at 143. Now, what is the partial of P with respect to D evaluated at a weight of 140 and number of drinks 3? Well, you actually evaluated that in the last section, and it turned out to be approximately 0.0265. I think I called this function F before, but it's the same chart, same everything. So that's from the previous section. So all that's left to do is fill in this, the right-hand side of L of x, y, with the values that we just found. And if you do that, well, you know, I call it L of xy, but I suppose it would be L of WD, wouldn't it? Okay. So now if you fill it in, you get L of WD is approximately -0.0006 times W minus 140 plus 0.0265 times D minus 3 plus 0.08. And remember what that is. 0.08 is the value of P evaluated at 143. So this is your approximation. I suppose I could have used just an equal sign here, because when we use the notation L of WD, that is our linearization, and the idea is that P then of WD is approximately equal to that linearization. So there it is.